and participants joining us for the International Virtual Faculty Development Program on Artificial Intelligence Empowered by Mathematics. We appreciate your interest and participation in this FDP. We hope this session will enhance your understanding of AI empowered by mathematics and foster valuable connections. Mathematics bridges theories and applications. AI is not a threat, but a partner for innovation. Experts bring depth and insight to enrich the learning. I now request Dr. R. Praveena, Assistant Professor, to introduce a speaker.
Thank you, ma'am. It is my honor and privilege to introduce Professor Yang-Hui He. He is a fellow at the London Institute for Mathematical Sciences. He also holds honorary positions as tutor in mathematics at Merton College, University of Oxford, visiting professor at City St. George University of London, and Changjiang Chair at Nankai University. Yang read Physics and Mathematics at Princeton University, BA with honors, followed by the Mathematics, Tripos at Cambridge, MA with distinction, before earning his PhD in Mathematical Physics at MIT, Scholar and Presidential Award. After a postdoctoral at the University of Pennsylvania, he joined Oxford as the Fitzjames Fellow and an STFC Advanced Fellow. He has authoring more than 200 papers and several books. Yang works on the interface between geometry, number theory, and string theory. He was a pioneer using AI2 for mathematics in 2017 and wrote the first textbook on the subject, Springer, LNM, 2021. Yang is also a keen science communicator. His public talks have included a Friday evening discourse at the Royal Institution and the Dias Statutory Public Lecture. We are truly privileged to have him with us today. Welcome you, sir.
Thank you very much.
Thank you, ma'am. I now request Professor Yang to proceed on with the session.
Okay. Thank you very much for this kind invitation, and it's a great privilege to be talking to you. And I'm going to tell you a little bit about, I know this has been an exciting 5 days about the mathematics for AI. And in this talk, I'm going to tell you a little bit of the opposite of how AI can assist mathematics. So I've been thinking about how does one actually do mathematics. And in this recent review that I wrote for Nature, and a more earlier review that I wrote for a data science journal, I've been thinking about mathematics as a bottom-up, a kind of a formal logical system, a top-down as a creative and intuitive art, and meta-mathematics as a language. And I'm going to explain in this talk how what each of this direction is precisely, and how AI can help us in solving this in general. So by mathematics, I'm going to be quite loose with the term. So any kind of theoretical discovery that involves mathematics, I believe this kind of ideas can help. Now, let me begin, of course, by reminding you this is, it is well known that, of course, computers have helped us with mathematical research in enormous ways, such as by speeding up computations and in modeling. This goes certainly without saying. And since the very beginning of computers, people have been using computers to help with mathematical research. However, something that's perhaps less appreciated is the fact that there are an increasing number of theorems, major theorems in the land of pure mathematics, which could not have been done with computers. So, for example, the four-color theorem or the Kepler conjecture, these are very, very foundational problems in pure mathematics, have been reduced to case-to-case checks on the computer. So in 1976, Appel, Haken, and Koch proved the four-color theorem by using the computer, tens of thousands of cases. And this is a similar case with Kepler conjecture in 1998. So it's kind of interesting that we have already, by the middle of the 20th century, reached the stage of our civilization where fundamental theoretical results in mathematics could not be decided by humans alone, simply because we do not have the computational capacity. So, however, let's think about what AI can do for us, right? So now as promised, I'm going to talk about the three directions of mathematics that is usually done, right? So let me begin with what bottom-up mathematics means. So in the modern version of bottom-up mathematics really goes back to Russell and Whitehead. And of course, one could even say that this goes all the way back to Euclid, to the very foundation of what mathematics is. But nevertheless, the modern version I'm going to stick to is this famous book of Principia Mathematicas, which started in 1910 by Bertrand Russell and Alfred Whitehead. What this idea is to axiomatize mathematics line by line. Right? So in this book, famously, the authors used logical symbols to build mathematics. Only on page 360 do they prove that 1 + 1 is equal to 2. So it's a very formal way of doing mathematics. Now, there's a reason why this book didn't take off as much as it perhaps should have in mathematics, was that in 20 years' time, since 1910, Gödel and then the Church-Turing thesis proved that there are sentences, if you're just trying to treat mathematics as sort of this sequences of logical symbols, there exists sentences in mathematics whose truth value could not be decided to any order of logic. So this goes under the rubric of the incompleteness theorems or the undecidability theorems of Church and Turing. Now, I like to quote my very distinguished colleague, Professor Min-Young Kim. He says, the practicing mathematician really hardly ever worries about Gödel, because if you have to think about whether your theorems are decidable or not, then you're not going to make much progress. There are certainly undecidable theorems or statements in mathematics, but there are still trillions and trillions and trillions of interesting statements that one can make. For example, Pythagoras' theorem or Fermat's last theorem, which are decidable statements which are enormously interesting. So because of this two double negative of but and but, there is, despite the fact the Gödel and Church and Turing killed this Principia Mathematica program, a long tradition of so-called automated theorem proving. So this started in 1956 with the logical theory machine, which is actually one of the very first human computers ever built. I have no idea what they did, but it was a very, very large machine they built on plastic punching cards, which they were able to actually prove some of the early statements of Principia Mathematica. So this idea of the ATP has now developed into something much more today. What people have used now, the answer to this ATP today is what's called the MathLib program. So people have been using formal languages like Coq and Lean, and I highly encourage you guys to just look up, but they're all freely available online. One particular things I like to draw attention to is the Lean programming language. What Lean does, and this is championed by Kevin Buzzard and Davenport and of course Fields medalist Tim Gowers and Terence Tao, they're all using this Lean programming language. What this language is to take every single statement in mathematics and formalizing it into a computer code. And if the code runs, then your proof is correct. So you can see that why this is such an important thing. What in particular, Lean was launched in 2013, and within 10 years, by 2023, Lean has, using what's so-called the Xena project, taken the entirety of undergraduate mathematics. So it's not very much, but still hundreds and thousands of lines. It's on the order of about 1 million lines of code, which has every single proof of everything that we teach a typical undergraduate in an advanced undergraduate course. And they have checked that mathematics up to that level is self-consistent and correct. Of course, undergraduate level mathematics is only a tiny bit of mathematics, and it is still very much an ongoing project headed by the likes of Terence Tao and Tim Gowers to formalize all of known mathematics. And this is an extremely important thing. And so you can see where AI can help us in this direction. And I won't talk very much about this because I'm not as involved in Project Xena, even though I now run the Lean workshop, monthly workshop with Lean with Buzzard. So Kevin Buzzard is based in Imperial College, which is only a 40-minute walk from my office. So this is very much a vibrant community. Now, as promised, I'm going to talk about bottom-up, top-down meta-mathematics. Meta-mathematics is also very interesting, and I won't talk very much about it. This is doing mathematics without any understanding of mathematics, right? So what this means, for short of anything else, I'm going to call it meta, meaning that can you do mathematics without actually understanding anything, right? At some level, we can argue that maybe this is what students do all the time. Now, on a more formal level, this is the world of large language models for math, LLMs. So one of the early experiments that was done back in 2018, so we took the entirety of the archive, and actually to contrast that, we also took Times of India, interestingly enough, because Times of India is a freely available source for language training. And we took the titles of the archive and in order to train this kind of ideas. And metamathematics is interesting. So it gradually became accepted in science. One should do this. So there was a 2019 paper in Nature where they took the abstracts of material science and they essentially found hundreds and if not thousands of new reactions in material science, not by doing science, but just simply doing the language of science. And so this is actually very interesting, right? So in 2022, ChatGPT passed the Turing test. And in 23-24, these 2 years really is beginning with large language models for math. There have been all kinds of private companies, ranging from OpenAI to Epoch AI to DeepMind, Google DeepMind, where they're just by studying previous cases of linguistic data of mathematics, can you generate new math? And this is actually a very exciting area. So some of the highlights, AlphaGeo and AlphaGeo2 within 1 year can now get to silver medal on Olympiad, the math Olympiad, right? So this is actually very impressive. Within 1 year, they were able to solve problems and get actually a gold medal. AlphaProof is something that DeepMind is currently working on, which couples language models to this lean proof assistance. And then this is clearly where things are going right now. All right. So the basic idea is now, punchline is by February, in fact, by July of 2025, AI is approximately equal to the 12-year-old Terence Tao. So I mean, if you reach the 16-year-old Terence Tao, then you're really at the cutting edge of mathematics. This is how impressive not only AI is, but also how impressive Terence Tao is, right? So it got 28 points in the silver medal by February 2025, and in fact by summer of this very year, it's getting the gold medal. Now you may ask, but everything I've said so far is about, International Math Olympiad level, which is very difficult high school level problems, and undergraduate level mathematics. What about actual research level mathematics? So in December 2024, Epoch AI launched the Frontier Math Project problem, right? This project actually tries to benchmark how the likes of Gemini, Claude, and GPT can work on research level problems. And this is very interesting. It wasn't doing very well by December of 2024, but by March 2025, it already solved 10 to 25% of 300 graduate level problems. And that's very impressive, right? And please go to this website to just have an idea of how hard these problems are. So in May 2025, they flew in 30 of us to the headquarters in Berkeley for Tier 4. Now, Tier 4 is the kind of problems I would give to a colleague that I would write a paper on, and I would or give to an extremely advanced postdoc or graduate student. So this is really research level problems. And what's really amazing, the benchmark for tier 4 has just been completed a couple of weeks ago. And the benchmark has actually solved about 25% of these problems. So the take-home message here is that about 25% of math problems that you would write a paper on, research level math problems, that you know an answer to. So of course, the benchmark that was set up here is that you want precise numerical answers so that they can actually check very quickly. But the rough idea is that GPT 4.1 mini and now GPT-5 and the advanced reasoning capacity of DeepMind can solve about a quarter of research level mathematics. So this is extremely impressive, right? So, and all of this happened within 12 months. So you can read about the Scientific American and Financial Times coverage of this because it's so exciting. And it is not inconceivable in the next 5 years or so, we will launch tier 5, where language models will begin to solve open conjectures in mathematics. So please stay tuned. And this is certainly a very exciting area of mathematics. Now, and I said there are 3 directions I would like to talk about. The last direction is this top-down. Now, what I mean by this is, at some level, you can think about what problems can AI come up with, right? So obviously, bottom up is this building up layer by layer, sentence by sentence mathematics in terms of proving if you're given a problem. Mathematics is trying to understand meta-mathematics is trying to understand mathematics as a whole, as a language. But what about problem giving, right? How good can AI help us in giving a problem for mathematicians to work on, right? So that's actually something I'd like to talk mostly about, because this goes into goes under the name of conjecture formulation. Now, traditionally, one can argue that mathematics is always top-down. While math papers are written bottom-up, with definition, theorem, corollary, proof, etc. In practice, the way we do mathematics is always with top-down. We kind of gain intuition and gain an idea, gain experience by looking at lots of things that are simply not publishable. Because we doodle, we throw it into the bin, or we do something on the blackboard just to give us an idea of what kind of problems we should even work on, and then experiment with this to see what we can do. So here's the best example of what top-down mathematics is. This is I joke that this is the best neural network of the 19th century. Well, it's a human neural network called Carl Friedrich Gauss, who is one of the greatest mathematicians of all time. So Gauss, at the age of 16, simply did the following experiment, right? Of course, he wrote his paper in the opposite way, but what he basically did was in this top-down form. So he plotted the number of prime numbers less than a given number, real number x, and he just plotted this curve, right? Now, I want to emphasize, Gauss only had the prime numbers up to 100,000 or so. So he had to compute more. He spent weeks computing more prime numbers at higher and higher. Now, imagine how much that would be sped up today. If Gauss had access to our computer, where you can just list the first 1 billion primes in under a couple of minutes, you can see how mathematics could be accelerated in this way. But anyhow, Gauss plotted this thing. It's very interesting that he was plotting this kind of thing. Nobody really thought to plot this kind of curve since the time of Euclid, really. And he looked at this and he says, well, this is clearly x over log x. Now, how did Gauss know this is x over log x? In fact, Gauss invented regression and, in some sense, modern statistics in order to answer this question, because he was a genius. But this kind of intuition that this should be x over log x, the curve of best fit, was really invented to just trying to see what this is. You had to wait for 50 years before mathematicians Adamard and Delaval-Toussaint proved this fact. because complex analysis did not even exist at this time. Well, we had to wait for Cauchy and Riemann to invent complex analysis in order to give these guys an idea to prove this fact. So this is a beautiful example of intuition, experience, and experimentation before you even have a formal language of mathematics to address a problem like this. Something that's very similar is the so-called BSD conjecture, which is one of the is still open conjecture, which is due to Burton, Swin, and Dyer. And what these guys did in the 1960s is that they plotted on a computer certain things called ranks and conductors of elliptic curves, and they were able to raise a conjecture which is still open today. 60 years later, and in fact, it's a Millennium Prize problem, and it's still open, and nobody knows how to address this. And there's been progress along the way in the last 60 years, but there's a $1 million award by the Clay Foundation attached to this problem if you can solve it. So these kind of ideas is using intuition and experience and mathematical experimentation is actually an extremely useful and important idea. So based on this, the human, let's do an experiment, right? This is a perfect experiment that we humans can do, right? So for example, if I were to give you this sequence, you can probably tell me the next number is 0 very quickly. And indeed, that's true. This is a sequence of whether an integer is multiple of 3 or not. If I gave you this sequence, if you struggled a little bit, you can probably tell me what this is. And that's, I won't give you, in about 10 minutes or so, you can probably will tell what the next number is. This is a sequence of whether an odd integer is prime or not. Okay. This one is a little harder. If you look at it, it's probably very difficult for you to tell me what the next number is, whether it's 0 or 1. So what this number given is here is a shifted version of so-called Liouville lambda function. This is just the parity of the number of prime factors. So for example, let's see, I started here with let's see, 1, 2, 3, 4. So 4 is 2 squared, so then it's an even number, so that's an even. 5 it factorizes as 5, so it's an odd, and so on. 6 is 2 times 3, so they're even number factors, and so on and so forth. Now, I want to emphasize this sequence because if you can tell me with any kind of certainty, even more than 50% guess what the next number is in the billions range, then you will be able to break every single bank in the world. This sequence is equivalent to the Riemann hypothesis, and knowing a control on this sequence is actually there's a formulation of the Riemann hypothesis in terms of the sequence, and actually there are no theorems in mathematics which will tell you even better than 50% what the next number is. Of course, we can plot this sequence for the first couple of billion very easily on a computer, but we just don't know what the next number is. So very easy, kind of not so easy, and this is extremely difficult. So what the human eye can do is just try to spot some patterns here. Now, this goes under the question, in fact, it makes us ask, what is mathematics, right? And G.H. Hardy gives this wonderful quote and definition of what mathematics is. And in his Mathematician's Apology, he says, well, mathematicians, what we are, we're like painters or poets. We're makers of patterns, right? So it's kind of interesting, right? If you think about the world of AI, if there's one thing that AI can do better than humans, is pattern detection, right? So that's kind of interesting how these two ideas can meet. In fact, the great Indian mathematician Harish Chandra often thought about this conflict between bottom up. Well, he didn't use the words bottom up and top down, but he used it in the sense of intuition versus experience, and he thought about this a lot, right? In terms of what mathematical discovery is. So of course, Harish Chandra didn't have access to AI, but I believe now we're in the age where AI can certainly help us with finding new patterns in mathematical data and therefore help us in discovering new mathematics. So, for example, what one can do, I love this word platonic data is just come about, and this is the kind of data that's very different from data you would get from CERN or from cosmology, because this is data that has no error. This is mathematical data of the purest type, this data of this type, right? So what one can do, for example, is one can make a shifting window. Here's just take the sequence, right? And then take, say, the first 100, and then predict 101, and then shift. Take the next 100 and predict 102, and so on and so forth. What this allows you to do is to set up a binary classification problem with binary vectors. In fact, all of mathematics, in some sense, can be put into this way, because that's what Turing machines are. Now, you pass this kind of things to your standard neural network, and you can make all sorts of predictions, right, in a supervised learning environment, right? So, for example, I did this experiment for this one. The very first one, whether it's mod 3 or not, you get 100% accuracy very quickly. And I say should, because as long as your neural network has a linear layer, it'll do this. The prime Q is about 80% accuracy. Maybe it's learning some kind of sieve method, but the Lie over lambda, I could not break 50%. The second number is just chi-square, so you want both numbers to be as close to 1 as possible. This is very interesting. If in the last experiment you can do better than 50%, then you really have a good handle of the Riemann hypothesis. So it's just kind of very interesting to think about mathematics in this way. Now, how did I get into this field? I just want to briefly mention, because my background is in algebraic geometry and string theory, and what I've had since PhD days were databases of manifolds or Calabi-Yau manifolds. You don't have to worry about the details, which is a very prominent thing in algebraic geometry. And a typical computation under algebraic geometry is to reduce these manifolds to, after a lot of computation, it's very, very technical computation. I'm just going to show you this as a footnote, and to get some kind of integer or topological invariant. And what I fed into the machine in 2017 was just to pixelate this kind of images and then try to teach this as if it were a digit recognition problem, right? So that's kind of interesting that at some level you can think of algebraic geometry as an image processing problem, right? But then again, you can even argue that all of mathematics is an image processing problem, right? So since 2017, you can scan. I can't possibly put all of the names and pictures of my friends and collaborators I've made in exploring mathematical data since then. So you can go to this QR code and try to see their happy faces. But the only thing that's more fun than doing mathematics is making new friends in mathematics. So we've been mapping out different mathematical data from diverse fields of mathematics. So I'm very grateful to my fantastic students and collaborators that have made over the years in exploring this idea of top-down mathematics assisted by machine learning. And meanwhile, in 2018, I was commissioned to write a textbook on Calabi-Yau, which is a very technical thing on Calabi-Yau manifolds from geometry to physics. But because of this, I was thinking about this machine learning exercise, so I added this machine learning to it, and which just very coincidentally became the first machine learning textbook for pure mathematicians. It's kind of, as I said, the idea of mathematics for AI is an ancient subject, but the idea for AI for math is relatively new. So as I summarized in this review I recently wrote, and here's everything I've said so far, is you can think about top-down mathematics as image processing pure Platonic data in mathematics. And then you can think about bottom-up mathematics as natural language processing as you build up mathematics line by line. And in between connecting the two, you think about large language models or meta-mathematics, where you may or may not even understand what the underlying mathematics is. And in fact, you don't even have to be a mathematician in order to do this bit, because you can ask GPT to somewhat get involved in this direction. Now, given this AI-assisted discovery, and especially since ChatGPT passed the Turing test in 2022, it's kind of important how far we can go with AI-assisted mathematical discovery. So with my friend and colleague here in the London Institute, we wrote this correspondence for Nature based on this conference we organized with a whole bunch of people, including Buzzer that I mentioned earlier, at Cambridge. And it's how do we have a more stringent test than the Turing test for AI-assisted discovery? And it basically goes under the rubric of AIN for AI, where the A stands for automatic, in the sense that your discovery has to be generated by some kind of artificial intelligence system, whether it's a machine learning algorithm or a language model. The I has to be interpretable. If you have an AI-assisted discovery in mathematics, just because you tell it some neural network can do very well is useless to the mathematician. So it has to be interpretable in terms of an actual discovery. And finally, it has to be non-trivial in the sense that you have to actually get real mathematicians to work on it. So you can't just say, well, this is. You can imagine an AI system can raise conjectures trillions per second. Raise conjectures like 5 plus 7 is greater than 2, which is certainly correct, and it'll be automatic and certainly interpretable, but it's not non-trivial. So how do we distinguish that? So, and of course, you have to make Birch happy. We named it after Brian Birch. This is the Birch of the BSD conjecture, and Birch. We were inspired by watching this talk that he gave in here. But Birch is 90, well, maybe 95 now. So it's amazing we still have him, and so he's certainly one of the greatest mathematicians of the 20th century. And he is thinking about how AI can guide raising conjecture, since after all, he and Swinton Dyer raised their conjecture in the 1960s by playing with computers, which became one of the central conjectures in all of mathematics. Now, there have been various candidates of AI-assisted discovery in 2017. Strictly speaking, none of them have passed the Birch test, but I believe we're not very far from it. So, for example, the early experiments that I was doing with Hodge numbers and topological invariance, that was, even though the neural networks was doing very well, it failed the eye test, right? Because neural networks are very difficult to interpret mathematically, right? So that's not good. And there have been various ones. I won't bore you with the detail. I'll just highlight a couple. There is this one in 2022, which is this paper. I was not involved in this, but this is the DeepMind paper in Nature, and they were able to raise a conjecture automatically using knot theory, and it was interpretable because it was an actual formula, but it failed the end test because they were able to prove the theorem themselves within a month. So there have been various other ones. I mean, now there've been. I did a rough estimate. It's been over 200 papers since 2017 on AI-guided human intuition, and the closest that they have come to end test, a non-trivial one, is this one that we did with my collaborators, Lee and Oliver, and that's come to known as the murmuration phenomenon, which I'm going to focus on in the next 10 minutes or so. So, as I mentioned, I did some early experiments in machine learning guided number theory, and I didn't get anywhere with it. This Liouville lambda function I couldn't break the 50%. Then I joined forces with some data scientists on trying to get some handle on the BSD conjecture, and we didn't have any luck. And then I was very happy to make friends with Lee and Oliver, who are number theorists, and suddenly the accuracies improved from 0% to almost 100%. And then, so we knew there was a chance something is happening much deeper than the neural network. So let me explain what I mean by this now. So this is the 2022 paper I had with Lee and Oliver, which was finally published in last year in Experimental Mathematics, and it was featured by Quanta. We're very happy that the Quanta featured us as one of the major breakthroughs of mathematical breakthroughs of 2024. So let me just explain to you what the BST conjecture is. I understand this is a very mixed audience. So the BST conjecture is one of the deepest and most important problems in all of mathematics, and there's a $1 million price tag on it. So let's go way back to Diophantus. So this is Greek mathematics from the 1st century BC. So now, if I give you this equation, you can tell me, well, this is a quadratic polynomial in 2 variables, and this describes for you a circle. This is not a problem. Now, the more interesting question that Diophantus asked is, well, I know there are infinite number of points on the circle, but how many rational points are there on the circle? Well, for example, this one. Now, this is already very, very interesting, because it's not trivial at all to see that 3/5 squared plus 4/5 squared is equal to 1. It's kind of interesting that there exist such points. Now, in one of the Hilbert's problems in 1901 is to decide, if I give you a polynomial of this type, can you tell me how to construct all of the rational or integer points on such a polynomial? And it was settled within 50 years by Matiasevich, Robinson, and friends that this problem is actually Turing undecidable. There's no algorithm in mathematics that can decide whether a polynomial of such a type necessarily has any rational solutions of such a type. So this is the problem of Diophantus. It's extremely difficult. In the world of mathematics, it's very easy to construct geometric objects and to find complex numbers or real solutions of things like this. But once you're in the world of rational numbers or integer numbers, it's extremely difficult. For example, think about Fermat's last theorem, right? You can find many complex numbers on Fermat's or Fermat type, but once you're in the world of integers or rational numbers, which are just ratios of integers, we already don't know. I mean, and we know famously that it took hundreds of years to settle even Fermat's last theorem. Nevertheless, for the degree 2 case, the Pythagoras case, we know there is an infinite family of rational solutions. There's one parameter infinite family of such a type. So that's at least settled. Even if you change the 2 into 3, it's already hard. So this is now what's known as an elliptic curve. This is known as a circle, but now or a conic section. Here is already an elliptic curve is hard. So but the moment you change one of these two from a 2 to a 3, it takes 2,000 years of mathematics to decide whether there are rational solutions or rational points on such a curve. And it has enormous implications. For degree 3 things, it has, in fact, Wallis's proof of Fermat's last theorem is exactly by homing in on cubic curves of such a type. They were called elliptic curves. So what do we know so far? After 2,000 years of mathematics, we know from everything from, there's been so much input, right? From, there's a lot of input from Greek mathematics and then Babylonian mathematics. And then, of course, Indian mathematics played a major role in deciding Diophantic problems of such a type. And then Chinese remainder theorem. So every culture in 2,000 years just to contribute to this problem, right? So what do we know so far is that cubic curves of such a type, there is an R parameter family of infinite solutions plus some finite families. I won't get into details of this. And that's really the state of the art. We know this R is called the rank of elliptic curve. It tells you how many infinite families of solutions there are on cubic Diophantic problems of such a type. Now, since it's so hard to work over the rationals, the best you can do is to work over modulo prime, right? So this goes under vaguely is called the global to local principle of the work. Now, if you work modulo prime, for example, this is not true. 2 to the cube plus 4 squared is certainly not equal to 1, but modulo prime 23, it is equal to 1, right? So the remainder 23, they're both equal to 1. Also, this is true modulo 5. What Euler did, or Euler didn't really think about this problem, but what Gauss and lots of great mathematicians thought about, and it goes under the name of Euler coefficients, is to keep track of how many solutions are there modulo each prime, right? And that's what's known as the Euler. It's called the Euler coefficient for a given elliptic curve, which is a cubic equation in 2 variables. You count you collect the obviously the prime number p here, 23 or 5 or whatever. You add 1 to it and then subtract by the total number of solutions that are true modulo p. Now, it's important to think this way because this is now a finite problem. In the worst case, because you're doing modulo prime, there's only a finite number of cases you need to count, right? In the worst case, you count everything up to 23, right? And you see whether by brute force it satisfies this equation modulo 23. So yeah, you modulo 23. In the worst case, you only have to check 23 squared number of times to see whether there are solutions. You can just set up a grid. So that's what the Euler coefficients counts. It counts this grid count of how many things that actually satisfy this equation, modulo prime, and then you see the deviation from p plus 1. Now, the interesting part is that you can organize this into a generating function, what's known as an exponential generating function, with this AP coefficients in, right? I won't get into the details of this. So what happens is that if you collect this generating function, this coefficient, this numerator, if you take the product of all primes, it's some kind of analytic continuation. There exists an analytic continuation which defines an analytic function. So what this function miraculously has the property of is that the order of vanishing of this function is exactly equal to the rank. So let's recap. What do I mean by this? Now remember, for the quadratic, there's 1 parameter family. For the cubic, there's an R parameter family. The idea is the deviation modulo each prime number p, when you take this exponential generating function and then take the product of all primes, should know something about the order of the rank. This is the BSD conjecture. If you can prove that the order vanishing of this analytic function is exactly to R, you get $1 million. So far, we have case-by-case checks. We've proven it for various cases. And, Manju Bhargava got the Fields Medal for showing related results. It's quite amazing. There are at least 2 Indian number theorists who have gotten the Fields Medal for proving steps along the BSD conjecture. But so far, the full conjecture remains open. So what we did with, in this 2019 paper, we just simply tried to learn to predict rank from this Weierstrass representation form. But then I made friends with Lee and Oliver Postnikov in 2020, and then from 2020 to 2022, we started trying to predict this rank by looking from a point of view of machine learning. We took Euler coefficients up to the first, say, 100 primes, and try to predict what the rank should be. And instantly we got 99% accuracy, plus accuracy. So something deeply is going on with BSD. Of course, this has nothing to do with the Birch test so far, because we've raised no concrete conjecture. What we then did was to home in onto why is machine learning so good at predicting rank from AP coefficients? So to our knowledge, this was the first experiment that's ever been done in number theory that tried to use machine learning to predict rank. And it was doing so well, we were trying to dig under the hood why it was doing so well. So we settled down on a principal component analysis by projecting this high dimensionality problem of 100 primes, the first 100 primes, just down to 2 dimensions. And here you can see very beautifully the distribution of these Euler coefficients actually separated. So here's rank 0, rank 1, and rank 2. So that's kind of interesting. It's separated in a very predictable way. Why do we like PCA, the principal component analysis? That's because it's a matrix transformation. So Postnikov looked at these matrices, and he was only an undergraduate intern of ours at the time. He looked at these matrices and noticed almost all of these matrices were numerically non-zero on one column. So what does that mean? That means it's essentially taking an average. This is a very strange average because we're taking average of the Euler coefficients over different elliptic curves within a certain range known as the conductor range. And then we simply said something should be different about this average. And here's the plot for this average. And you can see why this is called the murmuration conjecture, because it looks like the murmuration of starlings that we see. It has nothing to do with the birds, but it just kind of looks like it. But at this point, we already passed as I said earlier, we've passed the eye test because we now have an interpretable formula. We took this and emailed some of the leading number theorists of our time, Peter Sanak, Andrew Sutherland, and so on, and asked them whether you have seen this before. Would this average give you this plot? And to our surprise, they didn't know, right? So that's interesting. So that means now it passes the N test, because here's a concrete interpretable result that came out of machine learning, and it's non-trivial N in the sense that the experts didn't know. It's since 2022, it's become actually an active field of research in mathematics. I won't get into I won't bore you with the details of further finer details of the murmuration conjectures, but this is still an open conjecture in general, and it basically generalizes the Chebyshev bias in the distribution of prime numbers. It is now a theorem for classes of L functions, and there have been papers in 23, 24 that prove parts of the murmuration conjecture. But we now believe that this is in general true, that this function there should be an oscillatory behavior for general L functions that exhibit this behavior that will tell apart the analogs of analytic rank. So this is interesting. So this is the first time, Antoine, that a machine learning guided experiment led to a concrete mathematical conjecture, which is still open, and hopefully somebody will complete the full proof of this in the near future. So just to summarize, over the past 3 centuries, we can see where we're getting at, right? Conjecture formulation in the 19th century was good enough for the human eyeballs of Gauss, right? In the 20th century, Birch, Swinnerton, and Dyer really they were using the early primitive versions of the computer in 1960s to raise conjectures. And in the 21st century, clearly AI is guiding us. So this included the knot conjecture of the DeepMind, our work on the murmuration conjectures, and then this new matrix multiplication, which is actually solved. So this doesn't pass the N test that was also raised by DeepMind. So the future of mathematics is clearly a combination of this bottom-up, top-down, and meta mathematics, all of which are currently, as we speak, being aided by AI. So inspired by this, just a little bit about the London Institute. So we're UK's only independent research institute modeled after the IISc in Princeton, but we're very happy to be based in the historical buildings of so you see how beautiful my office is. We're building this in this beautiful room where Faraday used to work, and this was founded in 2011 by Thomas Fink, who is a theoretical physicist, precisely to get researchers to do full-time research. And one of our 4 themes you can check is exactly this. This is AI for mathematical discovery. And very, very interestingly, that I should be talking to this audience, because we've just gotten the Indian Ministry of Education approval to launch a LIMS India program, the details of which has to be yet to be sorted. And of course, as always, this program can only be really launched with private donations from wealthy Indians, which we're working on right now. So just to summarize, where is the future of mathematical research? Well, so here's if you can't see this very well, here's a tiny picture of Terence Tao, who is I think it's openly acknowledged as the greatest living mathematician. But you can see this flow chart. You take papers, right? You take humans and AI in a top-down way. You digest it through some kind of large language model. You take papers from the archive, and then you can use conjecture formulation from Platonic data using human and AI. And then once we reach auto-formalization into MATLAB and the lean programming language, we can translate these kind of conjectures into concrete statements or concrete problems to work on. And then we'll use bottom-up using proof pathways of MATLAB under this auto-formalized way, and then feed such things back into the human to interpret the results, write up a paper with assistance of AI, and then go back to paper. So this is already beginning in the last couple of weeks or a month or so. This pipeline is already beginning to happen in mathematics, and in the future, I think we can generate many more ideas precisely in this way. And I think I'm very optimistic that the human is still going to be very much part of this human AI collaboration in terms of finding new mathematics. So thank you very much for your attention.
Thank you, Professor Yang. Gratitude unlocks the fullness of life. Thank you, Professor Yang, for an excellent session on applications of AI in various fields using mathematical models. Your expertise and way of explaining collective informations of bottom-up mathematics, top-down mathematics, pattern recognition, image processing, mathematical conjectures, and many more made the session informative and engaging. We appreciate your valuable time, effort, and the value you brought to our International Virtual Faculty Development Program. Thank you once again, Professor Yang.
Thank you very much. It's a pleasure. And I hope this LIMS India program will take off, and I'll keep you guys updated.
Thank you so much, Professor Yang.
Thank you.
Finally, participants, your energy and enthusiasm contributed to the success of our event. Thank you so very much for joining us. We wish you a fruitful and engaging experience tomorrow also.
Thank you.
Thank you, sir. A feedback link has been posted in the chat box. I request you all to fill the feedback form. Participants can leave the meeting once you fill the feedback form. Thank you all once again. Have a good night.
Good. Thank you, and enjoy the rest of your very nice conference.
Thank you so much. Thank you so much.
Thank you.
Take care, Professor Yang.